Hi, I'm Carl, and in this video we're going to look at questions 92 to 94 of section 3 of the purple booklet. So this question looks at isomers, in particular constitutional isomers, which are stable forms of each other that share the same groups, only in different positions. 92 says, what compound is the unstable 3,3-dihydroxypentane most likely to form? So if we drew out dihydroxypentane, we know there's going to be 5 carbon atoms from the name, and there's going to be an OH group on either side, and then lots of hydrogens, which I'll just leave off. Whenever we've got OH groups on an alkyl group, we can remember that there's going to be a reduction reaction which could take place that attacks one of the hydrogen atoms here and turns it into a ketone, where we end up with 5 carbon atoms and an oxygen bond here, and the hydrogen goes off to form an ion in solution, or will precipitate out with whatever has caused the reduction to take place. So we end up with this ketone of the 3rd carbon, which means the answer for this one, which is 92, is going to be 3-pentanone, because we have this ketone group on the 3rd carbon. So there's going to be 3-pentanone, which is answer B. If we look at 93 then, it says consider the N-alkyldiols and the N-dichloroalkanes, that is the N-alkanes that have 2 hydroxy groups or 2 chlorines respectively, compared with the number of constitutional isomers of the N-alkyldiols, the number of constitutional isomers of the N-chloroalkanes is what? So this is a bit of a confusing question because lots of new words that I know I certainly haven't seen before. But remembering what an alkyldiol is, it's just a hydrocarbon group with 2 alcohol groups, 2 OH groups, and an N-dichloroalkane. It's just a hydrocarbon group with N carbon atoms with 2 chlorines attached to it. From the paragraph we've been given, we've sort of been told 2 rules: that it's unstable for a carbon atom to have 2 OH groups on it. And so that sort of limits the number of positions that you can put these OH groups on. But with the example of chloroform, which is given in the question, it's absolutely fine to have more than one halogen, in this case chlorine. So that's okay. So there's more freedom with where you can put the chlorine atoms because it will be stable in whichever position you put it in. However, you can't have 2 OH groups on the same carbon atom or else it's unstable. And this is all just information I've got from the paragraph. So that means if you have a hydrocarbon chain with N carbons long, and we're just going to do 5, how many places could you put that OH group? Well, you couldn't put them both on the same carbon atom. But every other possibility, of course, if you had them on different ones, like with here and here, for example, it would be okay. But you couldn't put them on like this. So there's a limit to how many spots you can put the OH group on. But if we looked at, for example, a butane here, where we've got 4 carbon atoms, we can put 2 chlorines on the same one, but we can also put them on any other carbon atoms we like. It's okay, no matter where we put them. So we know that there's going to be a greater number of constitutional isomers, a greater number of spots where we can put these chlorine atoms on than we could if we were putting on hydroxy groups. But there won't be twice as many. Of course, we can just put an extra one on each carbon if there's already going to be a chlorine there initially, because of course having them both on the same one is fine, as we've talked about. Well, there's not going to be twice as many, because we still have all the other possibilities, which take up the majority of the possibilities. So there is going to be a greater amount, but it's not going to be quite as big as twice as great. And then the answer D, of course, doesn't make any sense because it doesn't depend on the size of the alkane. Of course, the more carbon atoms you have, the more options you have for where you're going to put this chlorine atom. But if you increase the number of chlorine atoms, increase the number of carbon atoms for both hydroxy groups and for chlorine groups, you're still going to have a greater number of positions for chlorine. So it's not going to be greater if you're depending on the size of the alkene. Instead, the answer in this case is definitely going to be C, just because there's more freedom as to where you can put a chloro group than an alkyldiol group. And then finally, 94 asks, how many stable constitutional isomers of N-pentanediol are there? So to answer this, we have to remember what our rules are. We can't have them on the same carbon atom. So if we had pentane, which looks like this, of course, I'm just leaving off the hydrogens, that wouldn't be a stable constitutional isomer. So that wouldn't be one of the options. Instead, there are 6 options which I've drawn out here that you can see. Might be worth trying to learn how to name them. For this sort of question, it's best just to try and play around with it and see how many you can draw out. I got 6, and it turns out that the answer here is B, which is 6 different isomers. As you can see, none of these are on the same carbon atom, so we're not breaking that rule that we came up with. But because there are 5 carbon atoms, there's plenty of other places for us to put the second hydroxy group, as long as they're not on the same one. So that was questions 92 to 94, talking about constitutional isomers. I hope that helped. Thanks for watching.